In this video series, we will discuss how to solve circular motion problems. This video series builds on the material introduced in my previous series on basic Newton's second law problems. If you find that these video explanations move too slowly, you can use the solutions documents to supplement or replace the video explanations. And you can use the table of contents in the progress bar to skip to particular topics in the video. Now let's try this circular motion problem. First, please pause the video and try this problem on your own. And now, let's discuss the solution to this problem together. Here's a summary of the solution for this problem. Let's discuss this solution step by step. Here are some keyboard shortcuts which you may find useful while you're watching the videos. What problem-solving framework should we use for this problem? Well, the problem involves circular motion, and circular motion problems can often be solved using the Newton's second law problem-solving framework. The problem mentions the concept of mass, which can be substituted into the Newton's second law equations. The problem also mentions the concepts of speed and radius. Those concepts fit into this formula for the radial component of the acceleration. And the radial component of the acceleration can be substituted into the Newton's second law equations. So, the concepts that are mentioned in the problem confirm that we can use Newton's second law to solve this circular motion problem. Here is a handout which provides a step-by-step method for applying the Newton's second law framework for solving circular motion problems. You can find a link to this handout in the video description box, and I hope that you will now print out this handout so that you can follow along with the steps as you are watching the video explanation. This problem has already provided us with a sketch, but in that sketch we should add the object's circular path of motion. Now, some circular motion problems deal with horizontal circles, and some problems deal with vertical circles. In this problem, the mass is moving around the pole in a horizontal circle. So here is how we could show the object's path of motion around the pole in a horizontal circle. In this portion of the path, the object is moving in front of the pole. At this point in the path, the object is moving directly away from you into the page. Then in this portion of the path, the object is moving behind the pole, and at this point in the path, the object is moving directly towards you, out of the page. You should write down what the question is asking you for, and when possible, you should represent what the question is asking you for with a symbol. The question is asking us for the speed of the mass. Speed represents the magnitude of the velocity vector. And we can symbolize the magnitude of the velocity vector with the symbol v, written without an arrow on top. When you write the symbol for a vector without an arrow on top, that symbol stands specifically for the magnitude of the vector. Check that all the given units are SI units. Well, this problem mentions units of kilograms and meters, and yes, those units are both SI units. Here's a summary of the steps that we have completed so far in our solution. This step isn't relevant for this problem because this problem is numeric, not symbolic. Now let's work on the free body diagram. You should usually draw a free body diagram for each object whose mass is mentioned in the problem. Well, this problem mentions an object which is referred to as a mass of 0.5 kilograms. So we're going to draw a free body diagram showing all the forces exerted on that 0.5 kilogram mass. In your sketch, you should indicate the object's current position in the circle. Well, the object was already drawn in the sketch that we were provided by the problem. So we should simply notice that the object currently appears to be located at the far right of our horizontal circle. Here is a general two-step process for identifying the forces for your free body diagram. First, we draw a vector to represent the object's weight. Next, we systematically ask what is touching the object. Well, this mass is being touched by the string. A force that's exerted by a string or a rope or a cord on an object is referred to as a tension force. So here in our free body diagram, we include a vector representing the tension force exerted by the string on the mass. Are there any other forces being exerted on this mass? Well, just ask yourself, is there anything else that is touching the mass besides the string? No, nothing else is touching the mass, and therefore there are no other forces being exerted on the mass for us to include in our free body diagram. Notice that for a circular motion problem, we use the same two-step process for identifying the forces in our free body diagram that we would use for any other Newton's second law problem. The fact that this is a circular motion problem doesn't affect the process for identifying the forces on the object. Now would be a good time to pause the video and memorize this general two-step process for identifying the forces for your free body diagram. The purpose of the free body diagram is to indicate the directions of all the forces on the object. Well, the direction of the weight force is always straight down. The direction of the tension force should be parallel to the rope, pointing away from the object. Well, parallel to this rope, pointing away from the mass, would be a force that points in this direction. So I've indicated that the tension force is pointing in that direction in the free body diagram. You should pause the video and make sure that you have these two rules for the direction of the weight force and the direction of the tension force memorized. Here's a summary of the steps that we just completed for drawing our free body diagram. Now let's work on the force table. The purpose of the force table is to organize the data which we will need to substitute into our Newton's second law equations. Here's the outline of our force table. We'll begin with the first row. The purpose of the first row of the force table is to indicate the magnitudes of the overall vectors. Now, remember that if you write a vector symbol with the arrow on top, that symbol stands for the complete vector. But if you write a vector symbol without an arrow on top, that stands just for the magnitude of the overall vector. So in this first row, we write the symbols W and T without arrows on top to indicate that the purpose of this first row is just to indicate the magnitudes of the overall vectors. On the other hand, in our free body diagram, we wrote the W and the T with arrows on top because the purpose of the free body diagram is to indicate the directions of those vectors. You should know that a magnitude is a number that can be positive or zero, but that can never be negative. Here's a general three-step method for how to represent the magnitudes of the overall force vectors in the first row of our force table. First of all, we notice that we have not been given a value for the magnitude of either the weight force or the tension force in the problem. Next, we remember that there is a special formula for representing the magnitude of the overall weight force. Here's that special formula, W equals mg. We can calculate that the magnitude of the overall weight force is 4.9 newtons, and we record that here in the first row of our force table. Next, we think about the tension force. The problem did not give us a value for the magnitude of the tension force, and there is no special formula for representing the magnitude of the tension force, so we simply represent the unknown magnitude of the tension force by a symbol. We can simply represent the unknown magnitude of the tension force on this problem by the symbol capital T, written without an arrow on top, to indicate that this symbol stands specifically for the magnitude of the tension force. Notice that for purposes of our force table, we have not tried to figure out how the weight force will interact with the tension force. The Newton's second law equations will figure out that interaction for us later in our solution. You should pause the video and memorize this three-step method for representing the magnitudes of the overall force vectors in the first row of your force table. Before we can break these forces into components, we must choose our axes and positive directions. For a circular motion problem, we should choose a radial axis that points towards the center of the circle. Now, in this sketch, the object is represented as being at the far right of the circle, so the direction from this point that points towards the center of the circle is to the left. So here I've written down a radial axis that points to the left. So for this problem, the radial axis will be the x-axis. And then I've chosen a y-axis that points up. So for this problem, the x-axis can be referred to as the radial axis because the x-axis is pointing along the radius of the circle. And we can describe the y-axis for this problem as pointing perpendicular to the plane of the circle. In this problem, the object is moving in a circle in a horizontal plane. So since the y-axis is vertical, the y-axis is perpendicular to the horizontal plane of the circle. Now, if you want to, for this problem you could also draw a third z-axis, which represents an axis that is pointing directly out of the page. For this problem, that z-axis could be referred to as the tangential axis, because the direction that points directly out of the page at this point would be tangent to the horizontal circle. It turns out, however, that for typical circular motion problems, we're not going to need the z-axis. So let's keep things simple and just stick with our x and y axes. By the way, the radial axis can also be referred to as the centripetal axis. Remember, for a circular motion problem, you should choose a radial axis that points towards rather than away from the center of the circle. And you should always write down your axes on your paper and label which of the axes is the radial axis. Now we're ready to start breaking the forces into components. The weight vector is anti-parallel to our y-axis, which means that we can use this simple rule to break the weight vector into components. The weight vector is pointing down, which is our negative y direction. So w sub y will be negative. W sub y will have the same magnitude as the overall weight force, and the x component is 0. It is crucial to include this negative sign in front of w sub y. Now, the tension force is neither parallel nor anti-parallel to either of our axes. So we can't use this rule to break the tension force into components. Instead, we're going to have to draw a separate right triangle and use the SOHCAHTOA process to break the tension force into components. Here's the process for breaking the tension force into components. Of course, if you thought it was easy to break this force into components, you could use the table of contents to skip ahead to the next part of the video. We're using horizontal and vertical axes, so we draw a right triangle with horizontal and vertical legs. The tension points up and to the left, so the components point up and to the left. Up and to the left are our positive directions, so t sub x and t sub y are both positive. I've labeled the 30-degree angle with an asterisk to indicate that in our SOHCAHTOA equations we will focus on that 30-degree angle at the top of the triangle, rather than focusing on this 60-degree angle at the bottom of the triangle. This leg is labeled as adjacent because it's adjacent to the 30-degree angle that we're focusing on. This leg is labeled as opposite because it's opposite to the 30-degree angle that we're focusing on. This side is the hypotenuse because it's across from the 90-degree angle. So in our SOHCAHTOA equations, the length of the opposite side measures the magnitude of t sub x, and the length of the adjacent side measures the magnitude of t sub y. The length of the hypotenuse measures the magnitude of the overall tension force. We were not given a value for the magnitude of the tension force, but that will not prevent us from breaking the tension into components. In the first row of our force table, we already decided to use the symbol capital T, written without an arrow on top, to represent the unknown magnitude of the tension force. So, in our SOHCAHTOA equations, we use the symbol capital T to represent the length of the hypotenuse. We use absolute value symbols in our SOHCAHTOA equations to indicate that the SOHCAHTOA equations can only tell us the magnitudes of the components. It's our job to add the plus or minus signs to the components in a separate step. We already decided that each component is pointing in the positive direction, so both components are positive. Now, for this problem, it turned out that we used sine to determine the x component and cosine to determine the y component. But there are other problems where you might need to use sine for the y component and cosine for the x component, so don't assume that you will always use sine for the x and cosine for the y component. Use the SOHCAHTOA process on each problem, as we've illustrated here, to correctly determine the components for each individual problem. If it was difficult for you to break the tension force into components for this problem, then it's important for you to practice that vital skill. I have another video series that goes into detail and gives lots of practice problems for the skill of how to break a vector into components. And you can find a link to that video series in the video description box. Now that we've determined how we're going to represent t sub x and t sub y, we need to substitute those results into the correct position in our force table, as I've shown here. Remember that it is crucial to include this negative sign in front of w sub y. If we forget this negative sign, we're going to get the problem wrong. So I suggest that you should always include a plus sign in front of every positive component, because that will help you to notice when you need a negative sign in front of a negative component. Here's a summary of the steps which we just went through for completing our force table. Now let's work with the Newton's second law equations. We write the Newton's second law equation for the x component and the Newton's second law equation for the y component. For a horizontal circle, like we're dealing with in this problem, you typically need to write the Newton's second law equation for the radial component, which is the x component for this problem, and for the component that's perpendicular to the plane of the circle, which is the y component for this problem. The sigma symbol means add. So on the left side of the equations, we add all of the individual force components. Be sure to include this crucial negative sign when you're adding w sub y. For m, we substitute the mass, 0.5 kilograms. If an object is motionless in a component, then that component of its acceleration is 0. In this problem, the object is moving in a horizontal circle. That means that the object is vertically motionless. The object is motionless in the y component. That means that the y component of the acceleration is 0. So we can substitute 0 for a sub y in our Newton's second law y equation. Because the object is moving in a circle, we can use this formula, which applies to circular motion. Can you say exactly what each of these symbols stands for in this equation? Here's the answer to that. This symbol stands for the radial component of the acceleration. The symbol v, written without an arrow on top, stands for the magnitude of the velocity. The magnitude of the velocity vector represents the object's speed. The symbol r stands for the radius of the circle. This is a formula that we apply to problems that involve circular motion. The radial component of the acceleration always points towards the center of the circle. So in this case, the radial component of the acceleration will point to the left. Since we saw that for this problem a sub y equals 0, in this case the overall acceleration vector also points to the left. Since we chose a radial axis that points to the left, towards the center of the circle, the radial component of the acceleration will be positive. We've discussed that it's a good idea to include a plus sign in front of a positive component. So, as a beginning physics student, you should choose a radial axis that points towards, rather than away from, the center of the circle, so that the radial component of the acceleration will be positive. Now we can substitute into this equation. In this problem, the radial axis is the x-axis. So the radial component of the acceleration is a sub x. We don't know what the object's speed is. In fact, that's what the problem is asking us for. So we will continue to use the symbol v, written without an arrow on top, to represent the object's speed. The problem tells us that the radius of the circle is 0.25 meters. Now we can substitute this mathematical expression for a sub x into the Newton's second law x equation. The Newton's second law x equation has two unknowns, capital T and v, so we're not ready yet to solve the x equation. The Newton's second law y equation has only one unknown, capital T, so we are ready now to solve the y equation for capital T. Our result is that capital T equals 5.66 newtons. Next, we substitute our result for t into the Newton's second law x equation. After we do that, the x equation now has only one unknown, v, so we're ready now to solve the x equation for v. Our result is that v equals 1.19 meters per second. Notice how I have arranged our math in two adjacent columns, with all the versions of the Newton's second law x equation in the left column, and all the versions of the Newton's second law y equation in the right column. This two-column approach helps us to keep the math organized. So you should imitate this two-column approach in your own work on Newton's second law problems. Now we're ready to answer the question. The question was asking for the speed of the mass. We've discussed that speed represents the magnitude of the velocity vector, and this symbol v, written without an arrow on top, stands for the magnitude of the velocity. We found that that's 1.19 meters per second, which I will round off in the final answer to 1.2 meters per second. Check to make sure you included units with your answer. An answer without units is wrong. Check to make sure you answered the right question and that you answered all parts of the question. This problem could have asked us for the tension in the string. Here's a summary of the steps that we went through for using the Newton's second law equations. Actually, we have one more check that we should make. We should check that our answer makes sense. Let's focus on whether our result for capital T makes sense. Does it make sense that our result for capital T was positive? Well, the symbol capital T written without an arrow on top stands for the magnitude of the tension force. A magnitude can never be negative, so yes, it makes sense that this result came out to be positive. Now, does the size of this result for capital T make sense? To think about that, it helps to use this version of the free body diagram showing the components for the tension force. Earlier in our solution, we decided that the components for the tension force point up and to the left. So in this version of the free body diagram, I've drawn the components for the tension force pointing up and to the left. Earlier, we calculated that the magnitude of the weight force is 4.9 newtons. Our result for capital T was 5.66 newtons. To check whether this result makes sense, let's use this result to perform one additional calculation. This additional calculation tells us that the magnitude of T sub y is 4.9 newtons. Does it make sense that the magnitude of T sub y will equal the magnitude of the weight force? Well, the weight force is trying to make the object begin moving downwards. In order for the string to prevent the object from beginning to move downwards, the upwards T sub y has to cancel the downwards weight force. So yes, it does make sense that the magnitude of T sub y should equal the magnitude of the weight force. In this version of the free body diagram, I've drawn the length of this arrow equal to the length of this arrow to reflect that relationship between these two forces. Now let's do a recap of our work on this problem. The purpose of this problem was to introduce us to the method for solving circular motion problems. We saw that many circular motion problems, such as this one, can be solved by applying the Newton's second law problem-solving framework. How do we adapt the Newton's second law framework so that it can be effective for a circular motion problem? Choose a radial axis that points towards rather than away from the center of the circle. Make sure that you write down your axes. Use this formula to obtain an expression for the radial component of the acceleration. In this problem, the radial component of the acceleration was a sub x. So we substituted this result in for a sub x in our Newton's second law x equation. And that's pretty much all that we had to do in order to adapt the Newton's second law framework for solving a circular motion problem. Other than what I just mentioned, our method for solving this problem was very similar to the method you would use for solving any other Newton's second law problem. The major steps for any Newton's second law problem are free body diagram, then the force table, and then the Newton's second law equations. Remember that for a circular motion problem, we use the same two-step process for identifying the forces in our free body diagram that we would use for any other Newton's second law problem. The key to this process is to ask yourself, what is touching the object? For any Newton's second law problem, it's crucial to think in terms of components. For example, before we were ready to work with the Newton's second law equations, we had to break the tension force into components. Make sure that you understand this SOHCAHTOA process that we used for breaking the tension force into components. Remember that we were not given a number for the magnitude of the overall tension force, but that did not prevent us from obtaining mathematical expressions to represent the two components. We used the symbol capital T to represent the length of the hypotenuse in our SOHCAHTOA equations. And that allowed us to obtain mathematical expressions to represent the components in our force table. You don't need to know a number for the magnitude of a force in order to break the force into components. And then we substituted those mathematical expressions for the components into the Newton's second law equations. Here's another example of thinking in terms of components. Notice how differently we treated a sub x and a sub y. On this problem, x was our radial component. So for a sub x, we used this formula for the radial component of the acceleration. Of course, this formula did not apply on this problem to a sub y. Instead, for a sub y, we noticed that the object was moving in a horizontal circle, but that the object was vertically motionless. The object was motionless in the y component, so we were able to substitute 0 for a sub y. How did we know what order to work with the Newton's second law equations? Well, we counted the unknowns. Originally, there were two unknowns in the x equation, t and v, so we postponed working with that equation. But we saw that at this point, there was already only one unknown in the y equation, capital T. So we began by solving the y equation for capital T. When we obtained a result for capital T, we were able to substitute that result into the x equation. At that point, there was now only one unknown in the x equation, v. So at this point, we were ready to solve the Newton's second law x equation for v. Again, notice how we arrange our algebra for the Newton's second law equations in two adjacent columns. That helps us to keep the math organized. And I encourage you to imitate this two-column approach in your own work. Did you find this video to be helpful? If so, you can support the videos by making a monthly pledge at my Patreon page. You can visit my Patreon page by clicking the link on the screen or by using the link in the video description box. Thank you.